So I hope everybody can see my slides. And yes, we'll talk today about memory analysis, which is a part of a forensics process. Short recap of the agenda for today. This will be 2 webinars. Today we will introduce you to the basic analysis steps with a short recap of the introductory process and how to import profiles and intermediate symbol files into Volatility 2 and 3. And then we start with the basic analysis steps about process analysis, network analysis, file systems, and a look a bit in other artifacts like the Windows registry or the bash history on Linux. So let's start right away. We've talked in this webinar series already about the forensic workflow, which starts with the identification and preservation of potential evidence. Then we've talked in our webinar about memory collection or memory acquisition, about how to get an image of the main memory of the computer, which is going to be analyzed. And we did this with either DD or with a kernel module like WinPMem or MacPMem or Linux Lime or LinPMem or whatever you use for acquiring memory. So, and today we will cover the next 2 steps, like here, the processing, which means we import the collected data into our forensic tools, which will be Volatility here. And we will start with filtering out unneeded data and information, normalization of data, and building timelines. And the next step, which we'll be covering only very briefly, is the review and examination phase. We will skip about the reporting. So one thing we generated alongside, especially for Linux, when we do memory acquisition, was generating volatility profiles or intermediate symbol files, ISFs, ISF as they called in Volatility 3. Without these additional information, we would have no idea what kind of data is at a given memory address. Is it an integer? Is it a float? Is it a string structure of some kind? Is it a pointer? And we don't know what it is. And of course, we also don't know what this simple data is used for. Is it part of a process control block, or is it part of in-memory data structures of a process? Is it a socket, a file, a directory, whatever? So we need basically the symbol table from the compiler. So this is the kernel symbol table. So in Volatility, this is with some indirectional intermediate steps called a profile. In Volatility 3, it's an intermediate symbol file. So these, when we have generated profiles for Linux or other operating systems, we have to import them into Volatility. This is not much of a problem with Mac and Windows, as there aren't that many profiles around, and you can get along with the pre-compiled and prefabricated lists from the Volatility websites. But for Linux, there is not much of a pre-made intermediate symbol file list. So we have to import these profiles or ISF files into Volatility 2 or 3. And this is really just a very simple step. Here's a recap how to build a profile on Volatility 2. And we then just copy the new profile into our Volatility profiles directory. I can show you that. It's here on Volatility plugins, overlays, Linux. And there we see, for example, 2 new profiles which we've added for this task. Same goes basically for the Volatility 3 intermediate symbol files. This is the process of generating the symbol file. It's done with an additional tool called Dwarf to JSON, which just extracts the symbol mappings from the kernel or the system map file. You may need a kernel file which has the debugging information still with it, which may be in a separate package, or you have to somehow extract it from the initial RAM disk. So there might be some additional steps which I've left out here because this is very distribution specific. So, and if you have that, you can either use the precompiled zip files, which you've downloaded, and put them into the Volatility 3 symbols directory, or we can generate subdirectories and put our generated JSON file, this one here, directly into the subdirectory here. Volatility 3 can read either from the zip file or from the subdirectory directly. I have a Volatility 3. So I can show you that. So it's in the symbols directory. As you can see here, we have the zip files, and we have also a subdirectory, for example, Linux, which has additional profiles, like one here for OpenSUSE 15.1. So by itself, that should be everything you should do to get the profile imported into Volatility 2 or 3. So and from here on, we can start with Volatility. And basically, there are two versions of Volatility for those of you who are not aware of this. Volatility 2, which is the older one, as can be inferred by the version number, and a newer one, which is called Volatility 3. Volatility 3 is based on Python 3, while Volatility 2 is based on Python 2. And so as Python 2 is a bit obsolete now, the development effort goes into Volatility 3. And however, it's since January 2020 still in a somewhat beta phase. Also, internally, the version for Volatility 3 is 2.03 or something. But Volatility 2 isn't obsolete now. It's not getting any feature updates anymore. Sometimes there are bug fixes, and the code is mostly still working fine. And you can have your Python 2.7 running underneath it, and works very well. And there is lots of plugins and functionality that has not yet been ported to Volatility 3. So, and if you want to use a specific plugin, you may have to resort to Volatility 2, or you have very old Windows versions like XP or even Windows 2000, which might be somewhat better supported on Volatility 2. So it's not obsolete. So for a list of the volatility commands on Volatility 3, this is very, very simple. You can just type in volpy or Python volpy -h for help, and you get the full list of all the commands. And as you can see, the naming is a bit more systematic for Volatility 3 now. Everything that belongs to Linux starts with Linux dot command name. Everything belonging to Mac analysis starts with Mac. Everything with Windows starts with Windows. And there are a couple of common commands like config writer, banner, framework info, ISF info, which work directly. On Volatility 2, this is a bit more involved. It's split over two commands, either the standard help, which gives you also a list of the commands, but not of the profiles which you have, or a more complete list. As you can see, here's Linux or Mac is not mentioned in the standard help desk, and all the Windows commands start without a prefix. So you need --info as an option. So it can generate you also the profiles list, which is imported into Volatility 2. So you can use that to check if your profile has been imported correctly. And you can also get a more complete list of supported address spaces and the plugins. And as you can see, the Linux stuff starts with Linux underscore, and Mac stuff starts with Mac underscore. So that's about importing profiles and a very, very short intro into Volatility 2 and 3. So let's start with a process analysis. Do we have a question, or is it somebody who's forgotten to mute his microphone? Okay. So there are two kinds of process listings, which we can show you. Please don't be afraid when I use quite old Windows XP images. They are a lot smaller than today's Windows 10 images, and so the commands are running a bit faster, and this is more suited for a live demonstration. So let's start with a Zeus infected image on Windows XP and start with a process listing. And as you can see, we have our list of processes with the virtual offsets, the process name, process ID, parent process ID, basically what you would get in a task manager or PS list command from sysinternals. So if you want this as a tree, we can of course use the PS tree plugin, which works quite similar to that. And we can also have a little more involved process, which is called PS scan. And this uses a bit of a different technique. The PS listing commands just walk the internal task list, which is maintained by the Windows kernel, or the task list by the Linux kernel. So, and this can be fooled with a manipulation of the kernel data structures. For example, you can remove the process from the list, but still have the threads linked to the scheduler. And so the threads of the malicious process will still run, but it will not show up in any kind of process list. And for that, we have something that is called PS scan, which uses a process called carving, which just means we scan the memory for data structures that look like process control blocks. So we are basically starting to look for bit patterns. This is something that cannot be easily fooled by adversaries, because they have to use a working process control block, or their processes won't be scheduled. So if they want their malware to run, they still have to supply a working process control block. It also has the advantage of finding dead processes, because when a process stops or finishes running, the process control block is removed from the process list. But as it is often the case also with file system data structures, the contents of that process control block are not overwritten, at least not completely, unless that control block is really reused for the next process, which is occupying that memory here. So we can find dead processes in this way, and this will help us even finding processes which may have stopped running some time ago. Of course, this is a highly volatile environment, and I think we don't have any processes. Oh, yes, here is one. Here we have one command exe and one VMIP exe, which have a finish time. As you can see, we have here only starting times with the process, and I see the VMIP is something I don't see here, but which has been stopping some time ago. So we can see that there has been one, and we can also see the process ID and also the parent process ID from which it was started. So that's a very nice thing to have when doing a process analysis, as we can even see dead things in the kernel. And there's a third one, which has not yet been ported to Volatility 3, and it's only available for Windows. PSScan and PSList, PS3 are also available for Linux and macOS. The cross-view technique is something that walks different link structures, either the thread table, the task table, or whatever else is available here. I'll come to this in the next slide. And the differences may be a hint of adversary manipulation of data structures. Although we need a bit of background knowledge here to avoid false positives. So as you will do your memory analysis, you will learn quite a bit. So I recommend having a good documentation of Windows internals here. So get the book from Mr. Rusinowicz here. Yeah, we have the standard PS list here. I think we should start with the cross view to give you an impression of what it looks like before I start explaining the columns. As you can see here, we have different columns: PS list, PS scan, which are just the listings as we have from the previous commands of the same name. Here it is. And so on. It just shows us if this is present in the proper structures. So, and as long as there's everything labeled true, we usually have to do it with the proper process, which is correctly linked. But as we can see here, also some that have false in some entry in some columns. So let's go back to this here. So we have another one that's called a thread proc, which finds processes by following them from the thread control blocks, which is very suspicious when PS list or PS scan columns show false here. We have also a scan of the CID table, which is another table which Windows uses to have track of processes and threads. And we have also another table or list, which is the children of the CSRSS exe process, which is, I think, the first or second process starting on Windows, which is really the something akin to init on Windows Linux. And so we can also see if this has been properly linked to them here. There are some system processes which are default false, like SMSS, exe, or system, which are the very first processes which are also started by Windows. I think we can see this here in the tree listing. Yeah, system is the very first one. SMS comes also, but CSRSS is also started by SMS SE and the WinLogin here. So that's a very short overview of what we can do with the process analysis. I will get into some more details about process address spaces and malware hiding there in the next webinar. So, but for now, we just get something here. Of course, we should have a look not also at the only at the process IDs, but also at the command lines, which may be suspicious, something like tempvi on Windows, or we see something like Notepad, which is working with some unfamiliar options. So the way to do this here is to use the command line plugin on Volatility 2. So I'll show you that here. And Windows and Mac OS have the PS AOX plugin. No, let me see if I have this. Ah, yeah, da. So here's one for a small image here. And as we can see here, this was my memory acquisition process. So I can see with which part I did this. Okay, there was nothing else running on that Linux system, so it's a bit boring. So, and the other part is the environment variables, which is possible to do with the Windows NVARS plugin or the NVARS command on Volatility 2. Let's see if that works. Just one V. As you can see, you get a very complete listing of all the variables, like the app data variables, or where its temp files are kept, and all the other things. Let's see, have we something like path here? Here's one. All the path extensions, which we might here. So that's the very first steps for process analysis, which is not too different from a live analysis, which we would use with something like PS or Task Manager or Task Viewer on Windows. So aside from the running processes, we might have a look at the network, which means we want to see what are the open connections on our systems. There are two commands for that because there's been some changes in the Windows networking stack. For old Windows XP and below, you have the connections plugin and the NetScan plugin for Windows Vista and following. And we have the NetScan and NetStat commands for the Linux and Mac world, which works quite as well. On Volatility, there has been a bit of Volatility 3, there has been a bit of a change in the command lanes. So on Volatility 2, NetScan shows us the active connections. On Volatility 3 is NetStat. And so this has been swapping names on Volatility 2 and 3. So let's see if we can do this. One go back. Connection. No active connections here. I can do this with another image. So at least we don't have any open connections here. So let's see if we can look for closed connections, which is also possible with the NetScan command. So let's try this on Linux. Maybe I can see something here. NetStat. As you can see, the NetStat command works a bit like the standard NetStat command on Unix does, but we can see here the connections to the SSH daemon. And let's see what the NetScan command does here for us. Come on. The Windows image is a bit larger, so it takes a little more time to run. And especially if we do a carving, which means we have to wait a bit for this. Don't be afraid if a volatility command doesn't immediately return, especially if you have a really large memory image, so something in the tens of or even more than 100 gigabyte. Some commands, especially the carving ones, may really take more than an hour or so to run. So plan your time a bit ahead and have something to do in the time in between if you do this analysis. So it really can take some time. It's probably not broken if it doesn't return after 10 minutes or so. But on a small machine, it should really work a bit faster. So let's see if I can give you a little more thing here. Yeah, so open sockets is another part. So here it starts with the even closed stuff and the proper control blocks. So I terminate this here to have a little more time for the rest, which is also coming up ahead. So let's talk about our file system analysis. So aside from everything else, we would like to know what files are opened by what process on our system, because this may give a good hint of malicious behavior if there are some processes which have links to open files which are not belonging to a process of that kind or name. So think of the SVZ host exe on Windows, which has quite a lot of instances on Windows, and there is often when the system is compromised, there's often something hidden in these processes, and the kind of open files or handles may give a hint about what's going on here. So let's see what happens if we call handles on an image here. And handles is just something that is named after the handles command from Windows XP, from sysinternals. And as you can see, there's not only open files, it also has all the other handles to practically any kind of object present on a Windows system. We can see events, we can mutexes here, so we can keys, which are registry keys that are being opened by a process. We can, of course, also see a file here. And as you can see, it's with a full internal path name, device, hard disk volume, so-and-so, and even other things. We can have a way to narrow this down to a specific object type, which is possible with a -T option. So, and if we just want to have, for example, files, we can just narrow the search down, and it will give us only files. We could also pipe the output through grep, but this is probably not that useful, because it would just scan for the pattern on the whole line. Was it files or file? It's called file. Yeah, volatility is very touchy about the kind of command line you give to this. Even the ordering may be sometimes critical. So if volatility gives you an error or just shows no output, check your given command invocation if you got the ordering right here, and especially with the options here, where the common option should go first then the plugin, and then the plugin specific options. Volatility 3 is a bit more forgiving on that part, but Volatility 2 is very picky about this. So we can also use a similar command on Linux. As we know, it's called lsof, lists all open files. And again, this will also find socket structures. And as you can see here, it's the PID, but also the file descriptor ID. And we can see here systemd has, being the first process it has all its standard in, standard out, and standard error put to def null. And as we can see, all the other systems are out. So yes, on a busy system or a large system, these listings can be very, very long. Be prepared for that. So, and best pipe that output to a file so you don't have to run commands over and over again, or just directly import this into your, for example, autopsy or other tool you use for analysis, as you don't have to run all these stuff again and again. So there's also a way to look for temporary file systems. On Linux, we have temporary file systems which are kept in memory. So it's they don't have any disk backing here. So that means the contents will be lost on reboot or power off. And adversaries often use these as at least temporal storage for their stuff, for example, compiling things or preparing stuff here, because they know these temporary file systems are often not searched or conveniently lost on a reboot, and this is very simple. So this is a two-step process which starts with just getting a list of the temporary files, or more properly the mount points which are being used for this one. Let's see if that goes. Takes a lot of time to run. Here it is. And as you can see, there are several ones. Def shared memory is one of the classics. We also have 3 temporary file systems which are mounted under run, and also one on the C group plugin. Unfortunately, I can't show you this here, how to dump this, only as a dry season, but at least on my images, Volatility 2 crashed on me here, so sorry for that, but I'll supply you this. So you can just dump the file system to a local directory and then examine that files regularly in the directory. So you can use this as an add-on to your autopsy process, which will be covered by Toby in the sessions after the memory analysis. Then we have the other artifacts. We know the Windows Registry, which is a great source of forensic information, and there are very good tools to analyze registry files on disk, which is RegRipper comes to mind here, or even some other commands which have been built into other incident management tools. So as a recap, Windows Registry is separated in hives, which are starting with H something in your registry editor, and they are loaded from backing files into memory. And the keys are then always read and written from memory, never from the files directly. So, and when a key is changed, it's marked volatile and then later saved back to the backing storage file. So, and that means if I manipulate these structures directly as an adversary, I can change a memory key in memory without making them marking them as volatile. So they are not written back to files, and our persistent storage analysis wouldn't find this. However, that key is lost on reboot, so that might be not something the adversary had in mind, but we have to have this, keep this in mind. But we can also find these hives in main memory with our volatility tools. And so we could just start with the hive list. So show me the hives which are imported into memory. List. Yeah, live demos. So, and as you can see, we have the virtual offset and we have the backing storage file. We can also have a hive scan, which looks also for previously imported hives. We may do this so we can have a bit of a longer list. So, and then we can use the print key command to print a single key or even a version run, for example, the auto run keys on the registry. If we use this without a option for an offset, which we could use from here, for example, to use the, I think this is called config software, then we can narrow down the search to a specific hive. Otherwise, it would scan through all the keys on the system. And as you can see here, we have some auto run systems with a little legend, which is here. So if it's S, it's stable, so it hasn't been modified. And if it's marked with a V, it's volatile and has been changed. So as you can see here, there's one thing which is running additionally to the VMware stuff on a system start. So that's basically all we need to do for Windows registry analysis with volatility. So there are a couple of more commands which I will be just showing you. There's the get service sits, the LSA dam, the shim cache, the shutdown time, or the user assist plugin. So there's a number of plugins which help you with the specific analysis tasks on volatility. Volatility 3 has a few more plugins, but unfortunately they don't have something like get services or LSA dump or shim cache, but they can list registry certificates, for example, which is not present in Volatility 2. So it's a good practice to use both tools and try to analyze this with as many plugins as you can, and have to get a more complete list of the information. So another thing we have present on Linux as a source of information is the history. Almost all users use the bash as the shell. So it's a useful source of information because we can get some listings here. Let's see if, here it is. Now, let's start with a process list and grab for bash. So we can see we have two bash processes here running, and the bash command itself gives us a view of the proper command history. I will start with that one. I know this has been a very, very long history. Let's see. Come on. You can see here. It's a very, very long list. That's because this is a very long running session here where I have been doing all kinds of stuff. And as you can see, it just doesn't have only the command with all its arguments. It also has a timestamp when that command was entered. Bash keeps this timestamp internally, even if it's not written to disk, it's there. You can have a hist file stamped environment option, which gives us the opportunity to write this also to the history file. And if you unset the history file, this doesn't keep the bash from still keeping the history in memory. And I'll show you this with the other process ID, where I've tried this, and let's see. Just as a remember, this broken stuff here are just escape sequences from the cursors I used to step through the history list or the command line computing, which is sometimes when I accidentally hit return or so, and then I get a bit of garbage on input for the bash history. So as you can see, we have a few entries here, and then we look at it here. We unset the history file, then do some more commands, and as we can see, it is still present in the memory of the bash process. On the other hand, we really turn it off, set plus O history, it turns off the history completely, and then it's really no longer present, as bash doesn't keep this internal data structure. So also a nice way is to have a look at the environment structures, or even the internal command hash, which is another thing when the bash is doing. Stop that, it's not. We can see which commands have been entered, even if there's no history. It internally keeps a hash table like the C shell does for all the commands that have been entered and found here. So we can even see if there's just a command without a path on this line, we can see what's been present here. For example, if I call PS, I can see which binary has been called for that. So same goes for the environment variables. I'm a bit running out of time, so I don't talk about this. I just try these commands out. Some of them may not work with every image, so that's a bit sad. So if you'd like to improve volatility on that part, please do it. Would be better spent on volatility 3, of course, but yes, let's do this just here. So as I'm nearing the end of my talk for today, just to give you a short wrap up before we can take a question. I hope I could have been showing you that the basic memory forensic analysis can be done with the quite simple commands. You don't have to remember a lot of options or memory offsets or stuff like this. You can even do some very basic analysis without having to remember a lot of commands. And neither do you need some deep reverse engineering or malware knowledge, at least not for these very simple tasks. You need a bit of a solid background about the operating system and how it works. But again, we don't need a very deep knowledge of the internal kernel data structures or how these things work, but we need to know how processes and sockets work, but this is not something we need. So we can, with a basic knowledge of a sysadmin, you can do forensic analysis of a system, even forensic memory analysis. It's not so hard. Of course, it gets harder and harder if you do more advanced analysis, and you need then much more knowledge. But for the basic tasks, this can be done with very little advanced knowledge. Volatility 3 is promising, although I haven't shown you much of it, but Volatility 2 can still do most of the jobs. So hope you enjoyed that session, and I'm ready to take some questions. Let me just stop the screen sharing and see what's in the chat.
Great, thank you very much, Klaus. Yes, yeah. Nicholas Kirsten's got a question about volatility commands.
Yeah, Mr. Kirsten asked, is there a chance of missing suspicious activity if these commands take this long to complete? Well, if you take your time and let it run in the background overnight, for example, I'm pretty sure that will be finishing, and then you don't miss any information. But of course, if you get impatient or if your time budget isn't that large, yeah, then of course we have to cut this at some point and say, okay, we can't do any carving here. But there is also a bit of a trade-off, always a bit of trade-off if we do forensic analysis and have a limited time budget. And if we see that we might get some information, this depends then on your own needs and or the needs of the organization that is ordering the forensic analysis, if they are willing to put in some more time and wait some more time. It's not really much of your work time here, but you just have to say, okay, I start this, I let this run overnight or even of a couple of 1 or 2 days and see if the carving comes up with something useful. So this depends a bit on how you get your internal process and how the whole incident process handling comes along.
That's always going to be an issue that, you know, the tiniest thing can be swamped by huge quantities of data elsewhere. So yeah, absolutely, we have to accept that kind of thing. Yeah.
So any more questions?
Okay, that's great. Thank you very much, Klaus. Oh, one more. Ibrahim's come up with one. What's the recommended way to isolate a system from the network without losing the memory?
From a network, yeah, that's a bit touchy. So we can still pull the plug, the network plug in this regard, but that's a bit of well, the memory acquisition process usually doesn't take that long. So if you can afford having this run for 5 minutes or even maybe 15 minutes or so, depending on how long your acquisition process takes, I would just say, let it run, take the memory, and then cut off the system. And on the other hand, if that is really an issue because it's very large or you have a very slow medium to dump the system on, yeah, then you have to maybe block off the system in a firewall or block it off in a switch, so the interface at least is not yet going down. So you may have a bit of a time window while the sockets will time out, but the network connections will time out, and then we'll have to go and find them by carving.
Okay. Yes, as Andreas said, forensics is incredibly time-consuming, and patience is a virtue.
Yes, of course.
Yeah, impatient. You can easily miss something by being impatient, which is why I'm not a forensic analyst at all.
Don't drink too much coffee in between, so it just makes you twitchy. So better use some Camille tea or something else.
Yes. Attention to detail and patience are two of my skills which I lack massively. So yes, absolutely, I can understand it. That's why I'm here, merely pushing buttons and listening in awe rather than actually doing it myself. Thank you so much, Klaus. This has been great. We'll close it down now to really have a bit of a break for the next meeting, because I'm sure we all have meetings back to back. So thank you so much. The recording will be made available very soon once we've got it uploaded. And
also, of course, made the slides available as a PDF.
Perfect. That's fantastic. Thank you all. And I shall see you all next week. Thank you then. Goodbye.
Bye-bye.